we had started our new unit, that is MOSFET, and in MOSFET in the last lecture we had seen the different types of MOSFET, and in detail we had seen the construction and working principle of N-channel DE MOSFET. Depletion type MOSFET is also known as DE, means depletion enhancement MOSFET, because in depletion MOSFET there are two modes of operation, or depletion MOSFET operated in two modes, that is depletion mode and enhancement mode. So that is called as DE MOSFET. In today's lecture we are going to see the another type of MOSFET, that is N-channel enhancement MOSFET. The basic difference between the enhancement MOSFET and DE MOSFET is, in DE MOSFET the channel is in between the two highly doped N regions, but here in enhancement MOSFET this channel is absent. So we will see the enhancement MOSFET. The enhancement MOSFET is also known as E-MOSFET, and it is called as enhancement MOSFET because it can be operated in enhancement mode only. Here the construction of N-channel enhancement MOSFET is shown. We can see here it consists of a p-type substrate in which two highly doped N-type regions are diffused, which forms the drain and source terminal. This N-channel enhancement MOSFET consists of p-type substrate, and in p-type substrate the two highly doped N-type regions are diffused, which forms the drain and source. The two metallic contacts are connected for electric connection, and a thin layer of SiO2 is grown between the gate and the N-type channel or N-type regions. In previous lecture we had seen the metallization. Metal is deposited to provide drain and source terminal, and metal plate is deposited on the surface area between the drain and source, which constitutes the gate. Here we can see the metallization means metal is deposited here, which provide the drain and source terminals, and a metal plate is deposited between the drain and source terminal, which provides the or which constitutes the gate. The SiO2 layer provides extremely high input impedance of the order of 10 raised to 10 to 10 raised to 15 ohm. The chip area of MOSFET is typically 0.003 micrometer square or less. Likewise, we can construct the p-channel MOSFET starting with N-type substrate and p-type drain and source. In this only instead of p-type substrate we have to use N-type substrate for p-channel MOSFET, and here the heavily doped N regions are used. In p-type MOSFET the heavily doped p plus regions must be used. Now we will see the working principle of enhancement MOSFET. Power supply VDD is connected between drain and source, and gate voltage is made 0, that is VGS is equal to 0. In this figure we can see VDD is connected in between drain terminal and source terminal, and here VGS is connected to G is connected to ground, means we had kept VGS is equal to 0. Now VDD is applied and VGS is equal to 0. Since there is no channel in between these two heavily doped N regions, in depletion mode MOSFET, in depletion type MOSFET we had seen there is a channel in between these two heavily doped N regions. But in enhancement MOSFET, the channel is absent, and as there is no channel, so no current flows in enhancement MOSFET. So here when VGS is equal to 0, ID is equal to 0. Now applying VGS either positive or negative. So case first, VDD is applied and VGS is made positive. We can see in the figure VDD is applied and we had connected VGS, or we had made VGS positive, means we can see ground or negative terminal is connected to source, mean N region, and positive is connected here. So it makes the VGS positive. Due to the positive voltage at the gate, the minority electrons present in the p-type substrate are attracted towards the positive gate. Here we applied positive voltage at gate, and due to this positive gate voltage, the minority electrons which are present in the p-type substrate will be attracted towards the positive terminal, that is positive gate. So as VGS is increased, enough electrons will be near gate, which forms the channel in between the source and drain. Here if we increase VGS, the enough electrons will be get attracted or accumulated at this terminal, and these make a channel that is called as induced channel. As it is not present or it is not made at the time of manufacturing, but it is induced. So or this appears when we apply the VGS or increase the VGS. So due to the minority electrons present in the p-type substrate, these minority electrons will get attracted towards the positive gate terminal, and it will induce a channel, that is induced N channel. Due to the VDD, electrons flow through the induced channel, and due to this VDD applied, the electrons will flow through this channel, through this induced channel. Hence with positive gate voltage, the drain current ID increases. Next is the case 2. In case 2, VDD is applied and VGS is made negative, and due to the negative gate voltage, the minority carriers will be repelled from gate. Since there is no channel, the drain current cannot flow and ID is equal to 0. Here we can see, if we apply VDD and make VGS negative, due to this negative, the electrons or minority electrons in the p-type substrate will get repelled from the gate terminal. Okay, and as there is no channel, the drain current will not flow. So ID is equal to 0. Thus for negative VGS, drain current almost 0. Similarly, the construction and working of p-channel MOSFET can be explained. It is exactly opposite to the n-channel MOSFET. Now the drain characteristics of enhancement MOSFET. There is some correction. This is the enhancement MOSFET. Okay. So we have to see the drain characteristics of enhancement MOSFET. The drain characteristics we had seen in the DE MOSFET also. It is the plot of ID versus VDS, VDS means VDD at different values of gate to source voltage, that is VGS. We had seen these characteristics in DE MOSFET also. Same the characteristics are we have to see in enhancement MOSFET. Here only we can see for negative VGS ID is equal to 0, so it will go into the cutoff region for negative VGS or below 0, and for positive VGS we get with increasing positive VGS the ID current will get increased. We can see here, we will see these characteristics are divided into 3 regions: cutoff region, saturation region and ohmic region. Okay, it has 3 distinct region. Cutoff region, when VDD is applied and VGS is made negative, no electrons there available for the conduction and hence ID is equal to 0. MOSFET does not conduct, and here MOSFET works as a open switch, that is this is the cutoff region for VGS is equal to 0 or VGS is negative. Okay, saturation region, in this region ID remains constant and does not changes with changes in the VDS, and MOSFET works as an amplifier in this region. For a particular value of VGS the ID remains constant. And ohmic region, in this region we can see the IDS increases with increase in the value of VDS. In this region ID is maximum. Okay, and hence MOSFET act as a closed switch in this region. So this is about the characteristics of enhancement MOSFET. MOSFET, and so we had seen here the the construction of enhancement MOSFET, working principle of enhancement MOSFET and the characteristics of enhancement MOSFET. Okay, so we will